Hello viewers, welcome to my channel. I'm Hasham Ali Khan. Last video I have completed fourth problem on this simplex method. So the minimization problem. If the objective is to minimize something, then we have to deduct the surplus variable and add the artificial variable. So these problems requires a lot of practice, lot of patience, and you must have the ability to manipulate the numbers. In that case only you can have the good command. So watch the video from beginning till end, don't skip in between and watch all the videos. So if you have not watched the earlier videos, I suggest you go to the playlist of my channel, select the subject operation research, select the videos of simplex method. Be perfect about the concept, start doing the problems on maximization, then come to minimization. Now fifth problem. Before starting the fifth problem, I expect my viewers to have a printout of the problems which I have given in the link under my description. Take the screenshot of the points which I have written, then I'll explain. Come on, see the fifth problem. Solved by simplex. Minimize z is equal to 3x1 plus 4x2 subject to constraints 2x1 plus 3x2 greater than equal to 90 and 4x1 plus 3x2 greater than equal to 120 and x1 and x2 are greater than equal to 0. So here whenever the problem is of minimization type, here we have greater than equal to type inequality. When the inequality is greater than equal to, then you have to subtract the surplus variable and add the artificial variable. So two surplus variables and two artificial variables we need. So this is the original problem given. Minimization. Minimize 3x1 plus 4x2 subject to constraints 2x1 plus 3x2 greater than equal to 90, 4x1 plus 3x2 greater than equal to 120 and x1 and x2 are greater than equal. Introducing the surplus and artificial variables, we can convert that LPP into a standard form for solving by simplex. The objective function 3x1 plus 4x2 as usual, plus here we have to add the surplus and artificial variable with a 0 constraint for surplus and m is the constraint coefficient for artificial variable. So 3x1 plus 4x2 plus 0 into s1 plus 0 into s2 plus ma1 plus ma2. So whenever the problem is of minimization type, take m plus m, right? Now subject to constraints 2x1 plus 3x2 minus s1 plus a1 is equal to 90. Similarly 4x1 plus 3x2 minus s2 plus a2 is equal to 120. Now non-negativity restrictions are x1, x2, s1, s2, a1, a2. All the variables are greater than equal to 0. That's it. Now an initial solution is obtained by taking x1 is equal to 0, x2 is equal to 0, s1 is equal to 0 and s2 is equal to 0. So that a1 will become 90 and a2 will become 120. That's it. Now we have to start with the first simplex table. It's very easy to make the first simplex table because we don't require any formula, no calculation, nothing. Only coefficients we have to take. How much is a1 here? 90. So a1 solution value 90 and a2 is 120. Cj is the coefficient of objective function. Here objective function coefficient 3x1. So x1 3, 4x2, x2 is 4, 0 s1, s1 0, s2 0, a1 m, a2 m. That's it. Now we take the coefficient of the constraints. The constraint coefficient are 2x1, so x1 2, 3x2, x2 is 3 and minus 1, s1 is minus 1 and a1 is plus 1, then 0, 0. Second constraint 4x1, 3x2, s2 is minus 1 and a2 is 1. Remaining all the values are zeros. That's it. Now we need to calculate the zj value. 90m, m into 90 plus m into 120. So 90 plus 120 is 210. 90 plus 120 is 210 m. 210 m. Here 2m plus 4m, it will become 6m. 3m plus 3m, 6m. Here m into minus 1 is minus m. M into 0 is 0. So it will become minus m. Here m into 0, 0. M into minus 1 is minus m. Here m into 1 is m. Here m into 1 is m. Cj minus Zj. Cj is 3. So 3 minus 6m. Here also 4 minus 6m. Here 0 minus minus m will become plus m. Like this. 0 minus minus m. So minus into minus will become plus. So 0 plus m is m. Here m minus m 0. M minus m 0. That's all. So the objective function is all the index row elements should be zeros and positives. There should not be any negative value. Already in the previous video I have explained you. For minimization type problem, the optimality test is all the index row elements should be zeros and positive. Note it down. If there is any negative figure, it is not optimum. We have to go for the next table. How to find out negative value? Because m value is there. Now we have to suppose what the value of m. M value means we will take, let m is equal to 10. M is equal to 10. Why I am taking 10? Because 10 is greater than 3 and 4. Any value you can take which is greater than 3 and 4. That value is m. So you can take 5, 6, 7, 8, any value. But I am taking here 10. Because it is easier to calculate when m is equal to 10. So first is 3 minus 6m. So 3 minus 6 into 10. 3 minus 60. It is equal to minus 57. Second one, 4 minus 6m. So 4 minus 6 into 10. 4 minus 60 is equal to minus 56. Minus 56. So whichever is most negative, the most negative is minus 57. That means this one. So this is the entering variable in the next iteration. In the next table, x1 will enter. Now which variable will depart? It depends on minimum ratio. And the formula for minimum ratio is solution value divided by intersectional element. Solution value is 90. 90 by 2 is equal to 45. 90 by 2, 45. 120 by 4. 120 by 4. 4 3 is a 12, 30. So whichever is lower, that is 30 is lower. So which variable will depart? A2 will depart. So in the next iteration, x1 will enter and A2 will depart. So here I have written x1 enters and A2 departs. That's all. Now we need to calculate the values of the entering variable. Which is the entering variable here? Entering variable is x1. So x1 is equal to values of departing variable. Departing variable is A2. And one more thing you note down. When a artificial variable is departed, that column we don't require. So here A2 is departed. So we don't require A2 column. We need only A1 column. Right? Now, so what are the values of here? We will take A1 as it is. Then in place of A2 we are going to write x1. So A1 coefficient is m, x1 coefficient is 3. Now we need to calculate the values of x1. A2 value. A2 values are 120, then 4, then 3, 0, minus 1 and 0. These are the values divided by intersectional element. The intersectional element is 4. We are taking 4. The 120 divided by 4, 30. 4 by 4, 1. This 3 by 4. This is 0. This is minus 1 by 4. This is 0. That's all. These are the values of the entering variable x1, right? So the values are 30, 1, 3 by 4, 0, minus 1 by 4 and 0. Now we need the values of A1 is equal to old values of A1 minus intersectional element into values of entering row, entering variable. So old values of A1, what are the old values of A1? 90, 2, 3, minus 1, 0 and 1. Minus, which is the intersectional element of A1? A1 is 2. 2 into. Now, what are the values of the entering variable? 30. 30, 1, 3 by 4, 0, minus 1 by 4 and 0. That's it. So now we need the values. 90 minus 30 into 2 is 60. That comes to 30. And 2 minus 2, 0. 3 minus 2 3s are 6 by 4. So if you take LCM 4, 4 3s are 12. Minus 4 4 get cancelled, 1 6 is 6. So 6 by 4 or 3 by 2. Here minus 1 minus 0 is minus 1. 0 minus into minus will become plus. 2 by 4 or 1 by 2. Then here it is 1 minus 0 is 1. We got all the values of A1. A1 values are 30. Then we have 0. Then we have 3 by 2. Then we have minus 1, 1 by 2 and lastly 1. After calculating this values, now we have to find out the ZJ value. So m into 30, 30m, 3 into 30, 90, 90 plus 30m. This is the value of ZJ. M into 0, 0, 3 into 1, 3. Now here you have to be careful regarding calculation. M into 3 by 2 is 3m by 2. 3m by 2 plus 3m by 2 plus 3 3s are 9 by 4. 9 by 4. If we take LCM 4, 2 2s are 4, right? 2 how many times cuts 4? 2 times. 2 3s are 6m plus 9. So it will become 6m plus 9 by 4. 6m plus 9 divided by 4. Here m into minus m, minus 1 is minus m. Here m by 2 plus into minus minus 3 by 4. Minus 3 by 4. LCM if you take 4, 2 times. 2m minus 3. So 2m minus 3 by 4. 2m minus 3 divided by 4. M into 1 is m. That's it. So we have calculated ZJ value. Now CJ minus ZJ is 3 minus 3, 0. 4 minus 6m plus 9 divided by 4. Here 0 minus m will become plus m. Then 0 minus 2m minus 3 divided by 4. M minus m, 0. That's it. Now we have to find out which is the entering variable. Optimality test, all the index row elements should be zeros and positive. If there is any negative value, it is not optimal. So we have to find out. Let m is equal to 10. Why I am taking 10? Because 10 is greater than the actual cost 3 and 4. Any value we can take. So to make calculations easy, I am taking 10. The first value is 4 minus 6m plus 9 divided by 4. So 4 minus 6 into 10, 60. 69 by 4. So how much? 69 divided by 4, 17.25. So plus 4 minus 17.25. So it will become 13.25 minus 13.25. And the next one, Which is the next one? 0 minus 2m minus 3 divided by 4. That is 0 minus 2 into 10, 20 minus 3, 17, 17 by 4. 17 divided by 4, it comes to 4.25. So it comes to minus 4.25. See here, two negative figures we are getting. The most negative is minus 13.25. For which variable? This. So x2 will enter in the next table. x2 will enter in the next table. These are the intersectional elements. Now minimum ratio, 30 divided by 3 by 2. 30 divided by 3 by 2 is equal to, here 30 divided by 3 by 4 is equal to, now 30 divided by 3 by 2, so into 2 by 3. So 3, 10, 10 to 20. So here it comes 20. Here 30 divided by 3 by 4. So 30 into 4 by 3. So it will come 30 divided by 3 is 10. 10 4s are 40. So 20 or 40, whichever is lower. 20 is lower. For which variable? A1. So in the next table, A1 will depart and X2 will enter. Now see here, we have completed table 2, simplex table 2, and we come to know that the next entering variable is X2 and the departing variable is A1. So now we are going to make the simplex table 3. Same columns, but when A1 departs, there is no need to open the column of A1. So only we need X1, X2, S1, S3. Artificial variable, once it is departed, there is no need to make the column, right? And this is the column. In place of A1, I am substituting entering variable X2. S1 remains same. The first thing is we want to find out the values of the entering variable X2. So values of entering variable X2 is equal to values of departing variable divided by intersectional element. In every problem we are applying the same formula, whether it is a maximization problem or minimization problem. So which are the values of the departing variable A1? 30, 0, 3 by 2. See here, 30, 0, 3 by 2. Minus 1 and half. Minus 1 and 1 by 2. We are not taking this 1 because we don't have the column of A1, right? Now divided by intersectional element is 3 by 2. So 3 by 2, 3 by 2 division. So 30 divided by 3 by 2. If we make it multiplication, it will become 2 by 3. So 20. 0 divided by 3 by 2, 0. 3 by 2 divided by 3 by 2, 1. Minus 1 divided by 3 by 2. So minus 1 divided by 1 into 2 by 3. So it will become minus 2 by 3. 1 by 2 divided by 3 by 2. So 1 by 2 into 2 by 3. 2 will get cancelled, 1 by 3. So we got the values of the entering variable X2. So here I am writing X2 values as 20, then 0, 1, minus 2 by 3, and lastly 1 by 3. These are the values of the entering variable. Now we need the values, new values of X1. So here values of X1 is equal to old value of X1 minus intersectional element into values of entering variable. Same formula we apply. So old values of X1 are 31, 3 by 4. 31, 3 by 4. 0 and minus 1 by 4. 0 minus 1 by 4. We are not going to take 0 because A1 is eliminated. Minus intersectional element of X1 is 3 by 4. So I have taken 3 by 4 in all cases into values of the entering variable is 20, 0, 1. So 20, 0, 1 minus 2 by 3 and 1 by 3. Now simplify. 3 by 4 into 20. So 4 5s are 20, 5 3s are 15. 30 minus 15 is 15. 1 minus 0 is 1. 3 by 4 minus 3 by 4, 0. 0 minus 3 by 4 into 2 by 3. 3 will get cancelled. So minus 2 by 4. No, minus into minus will become plus. Plus 2 by 4. So 2 by 4 can be written as 1 by 2. Similarly, minus 1 by 4 minus this 3 will get cancelled. So 1 by 4. Minus 1 by 4 minus 1 by 4 is equal to 4 LCM minus 1 minus 1 minus 2. Minus 2 by 4 can be written as minus 1 by 2. So we got the values of new values of x1. Now write on 15. Then we have 1, 0, 1 by 2, and lastly it is minus 1 by 2. Now we need to calculate the ZJ value. 2 into 4 into 20, 80, plus 3 into 15, 45. That is equal to 125, right? 4 into 0 is 0, 3 into 1 is 3. 4 into 1 is 4, 3 into 0 is 0. So here remains 4. So 4 into minus 2 by 3, so minus 8 by 3. Similarly, plus 3 into 1 by 2, 3 by 2. So LCM, 3 2s are 6. 3 how many times cuts 6? 2 times. 2 8s are 16. 2 how many times cuts 3? 3 times. 3 3s are 9. So minus 16 plus 9 divided by 6. So it will become minus 7 by 6. Is it correct? Yes, 9, 10, 16. Minus 7 by 6. Minus 7 by 6. Here it is 4 by 3 and minus 3 by 2. Minus 3 by 2. LCM is 6. 3 how many times cut 6? 2 times. 2 4s are 8. 2 how many times cut 6? 3 times. 3 3s are 9. That is equal to minus 1 by 6. These are the ZJ values. Now CJ minus ZJ, 3 minus 3, 0. 4 minus 4, 0. 0 minus 7 by 6. So it will be plus 7 by 6. 0 minus 1 by 6. So minus into minus will become plus 1 by 6. That's all. So we have calculated the index row element CJ minus ZJ. What do you observe here? All the index row elements are zeros and positives. No negative value is there. So we reached the optimum solution. We reached the optimum solution. No further improvement is required. And the solution is x1 is equal to 15, x2 is equal to 20. And the minimum z is 125. So after completing this table, you have to write the conclusion. Since all the index row elements are zeros and positives, so we reach the optimum solution. The solution is x1 is 15, x2 is 20, and the minimum z value is 125. So this is the end of problem number 5. Totally 5 problems we have completed, in which 3 are maximization and 2 minimization. One more problem we'll do on minimization, then we'll come to the next topic, mixed constraints. So inshallah we'll continue the next problem in the next video.